Hi, I'm Shivani, a student from the Department of Computer Science and Engineering. I have chosen LeetCode's 40-second problem trapping rainwater for RECode, conducted by the Coding Club. LeetCode's 40-second problem, that is trapping rainwater, is a classic algorithmic problem that challenges your problem-solving skills and ability to design an efficient algorithm. It is very well known in computer science and also frequently asked in interviews in many companies like Intuit, Microsoft, Adobe, etc. The problem statement: given n non-negative integers representing an elevation map where the width of each bar or block is 1, compute how much water it can trap after raining. This is a difficulty level hard question on LeetCode. It's also available on Geeks for Geeks. There are 3 constraints mentioned. One is n equals height dot length. 1 is less than or equal to n, less than or equal to 2 into 10 power 4, and 0 is less than or equal to height of I, less than or equal to 10 power 5. So height of I has a cap at 10 power 5. These are some ways to visualize this problem. You could look at it as hills and valleys or buildings and blank areas where rainwater can be trapped, like the pictures given here. Different cases that you may encounter, basic and normal cases where, for example, you have 1, 0, 1. So you'd have water trapped in 0's place and input less than or equal to 2. In this case, rainwater cannot be trapped because you only have 2 blocks and there's no space for rainwater to be trapped. Flat or same height, all the blocks are of the same height, so there are no dents or valleys or low areas where water can be trapped. Empty input, in this case you return 0. Input with extremely large heights. So here we can take the minimum of height of I and 10 power 5 to cap the heights at the maximum allowed value. If the input contains float values, you can convert all the values to integer or float as required. Input containing non-numeric values. In this case, we raise an error to prompt the user to give only numeric values. Input with negative numbers. In this case, we have to specify whether we are going to consider the height as 0 or to include the negative height in our calculation as well. For this particular LeetCode problem, there are some conditions defined already. The input is going to be non-negative and the integers have the constraints as mentioned in the previous slide, and the width is always going to be 1 for each block. Here's a sample test case where we have the input and output given. Here you can see each black square or block represents the elevation and the empty areas are where the rain is going to be trapped. So here one unit is going to be trapped, here 1, 2, 3, 4, and here another 1 unit is going to be trapped. So totally we have 6 units of rainwater being trapped. This is a better visualization of the previous slide. As you can see, 1, 2, 3, 4, 5, and 6. Imagine you have a row of blocks and each block's height represents the elevation of that spot. So you have a row of blocks, which is what is given in the array, and each block's height represents the elevation. So you have 0, 1, 0, 2, 1, 0, and so yeah, so you have 0, 1, 0, 1, 2, 2, 1, 0, and so on. When it rains, water accumulates in the low spots or valleys between the blocks, which you can consider as hills. The goal is to figure out how much water can be trapped in the low spots. When it rains, 6 units of rainwater get trapped in the low spots between the blocks for the given test case. The 2 approaches we will be exploring in this is brute force and 2-pointer. In brute force, you consider each element as a potential pit or low area and calculate trapped water for each element. Here the time complexity would be n squared, and 2-pointer is where you maintain left and right pointers and you move them towards each other, tracking the maximum heights and calculating the rainwater or trapped water as you go along, as you traverse. The time complexity is O of n. Brute force. In this, you initialize a variable rain to 0, that is no rainwater is trapped yet, and then you loop through each block in the elevation map. So for each element in your array, you traverse through it, you loop through it, and you do it except the first and last ones because they cannot trap water. So if you see here, you cannot trap water on this side as there are no blocks towards the left of 0 and there are no blocks towards the right of n minus 1 or n, whichever way you count it or index it, from 0 to n minus 1 or 1 to n. For each block at position I, do the following 4 steps. First, find the highest block to the left of I, including I, and store it as left max. And then find the highest block to the right of I, including I, and store it as right max. And then calculate how much rainwater can be trapped for that particular I. If trapped rainwater is positive, it means you can trap water there. Add it to the rain variable. Loop through all the blocks and return the rain variable, which now holds the total trapped rainwater. This is the code for it. So you start with initializing n equals height dot length, rain equals 0. You traverse through the array from 1 to n minus 1 because you are not taking the first and last element, as they cannot be trapping water. You set left max and right max equals 0, and then for int j equals I, that is from ith position, you calculate which is the left max by looking at all the elements to the left of your current position. So you do j equals I, j greater than or equal to 0, j minus minus. You decrement and find the left max. By using the math.max function, you have the left max and height of j argument to calculate it. Similarly, you do the same for right max, where you have right max equals math.max right max comma height of j. And then you calculate rain by taking the minimum of left and right max minus height of your current position. And finally, you return rain. For this code, the time complexity is n squared because you have 2 for loops. It's a nested loop. This outer loop runs n minus 2 times, and each of this for loop and this for loop runs n times. And the rainwater calculation, this is constant. So together you have n square times complexity. The space complexity is O of 1 because we do not use any additional data structures or dynamically allocated memory, and that makes space complexity O of 1. A sample test case for brute force. Consider the input array 0, 1, 0, 2, 1 and 2 as the height of each block, and this is the visual representation for it. You start with rain equals 0 and you start at index 1, not index 0, because we saw that index 0 and the last index here, that is 5, cannot hold water, cannot trap water. We start with left max and right max equals 0, and then here in the first outer loop in here you start calculating the left max and right max, and that is how you calculate index 1's left max is 1, because you're considering this particular block including that particular position as well. So you have I equals 1, and to the right of I, to the right of index 1, the highest or right max is 2. So you set right max for I equals 2. Next is calculating rain. You take the minimum of left max and right max minus height of I. The minimum is 1, so you add 0 plus 1 minus 1 because height of I is 1, and then you increment I. By incrementing I, we have I equals 2. We saw that rain is still 0. For I equals 2, the left max is 1 and right max is 2. Minimum of left and right max is 1 and height of I is 0. Height of index equals 2 is 0. So rain is 0 from previous iterations rain value, 0 plus 1 minus 0, which is the height of index 2, which gives us 1. Rain equals 1. Then increment I. Now rain's value is 1. For I equals 3, after incrementing I's value, we are now at index I equals 3. For this, left max is 2 and right max is also 2. We take, we now calculate rain's value, which is minimum of left and right max, which is 2, minus height of I, which is 2. So you have 1 plus 2 minus 2, which gives us 1, and increment I. The value of rain is still 1, but we are now at index 4. Left max and right max is both 2. We take minimum of left and right max, which gives us 2, minus height of I, 1. So you add 1 plus 2 minus 1, which gives us 2. And we increment I. But now the outer loop's condition doesn't satisfy, as I is not less than n minus 1. Because I is now 5, n minus 1 is also 5, which doesn't satisfy. So we exit and return the rain value, which is 2. And it matches our output. For this code, on LeetCode, all the test cases passed. Pointer technique is a more optimal way to solve the trapped rainwater problem. Here you take two pointers left and right, which corresponds to the beginning and the end of your array or the elevation map, and here you initialize two variables, left max and right max, to 0, which keeps track of the maximum in the left and right sides. You initialize a variable to keep track of your rainwater, like the previous approach as well, and then while the left pointer is less than the right pointer, we do the four things here. We find the maximum height to the left of the left pointer, store it in left max. We find the maximum height to the right of the right pointer, store it in right max. Then we calculate rain at the current position as either left max or right max minus height of left or right. You take left max minus height of left if the height of left is less than height of right, else you do right max minus right. Move the pointer with the smaller height inward, left or right, depending on which side is shorter. Repeat the previous step, that is, while the left pointer is less than the right pointer. This loop is repeated as long as left is less than right, and then return the rain variable, which holds the total trapped rainwater. Let's solve this problem by typing it on the code editor in Java. First we take n's value, which is height dot length. Then this is an edge case that we saw. If n is less than or equal to 2, it cannot trap rainwater, so you return 0 and break the function here. Int left equals 0, right equals n minus 1, int left max equals 0 and right max equals 0, and another variable to hold rain. While left is lesser than right, left max equals math dot max of left max comma height of left. Similarly, for right max, math dot max right max comma height of right. Next we define an if loop here, if condition, to check which height is lesser. If height of left is lesser than height of right, we calculate it as rain plus equals left max minus height of left, and increment left to move to the next position, else rain plus equals right max minus height of right, and decrement right to move towards the left pointer. These loops are done. Now we return rain and run our code. And all the test cases have passed. The time complexity is O of n because we iterate through using the while loop, and the number of iterations is directly proportional to the number of blocks or elements in your array. The space complexity is O of 1, just like how it was in brute force approach. A sample test case. Initially, we start with left equals index 0 and right is at index 5. First, left max is 0 and right max is 2. As you can see, the condition here is left max equals maximum of left max and height of left or height of right for right max. So here it's maximum of 0 and the height, current height. For this it's 0, and so you have left max equals 0. It is supposed to be 0 here. Right max is maximum of 0 or height of this, so it's 2. Height of left is less than height of right, 0 is less than 2. So rain is 0 minus 0, which is 0, and left is incremented. Now left is at index 1 and right remains at the same position. Left max now becomes 1 but height of left is still less than height of right. So again you do 0 plus left max minus height of left. So it's 0 again, and you increment left. Left max is still 1, but and right max is 2, but height of left is still less than height of right. Again you have 0 from previous range value plus height left max, which is 1, minus height of left, which is 0. You get 1 unit is trapped so far, and then increment left pointer. Left is at index 3. Index 3's height value is 2, so left max is now 2. Since height of left and height of right are equal, we do the else condition where we calculate range plus equals right max minus height of right. So it's 1 plus 2 minus 2, which is 1, and right is decremented. Now left is at index 3 and right is at index 4. Height of left is greater than height of right, so again we do the else condition where we calculate range plus equals right max minus height of right. So you have 1 plus 2 minus 1, which gives us 2. 2 rainwater units are trapped, which is the answer. Now right is decremented. Here left and right are equal now, so you break out of the while loop and return rain, and at this point the output is returned and you get the final answer, which is 2. This is a summary of the tracing that we just did, and all the test cases passed as well. A comparison between the two approaches. In time complexity, the brute force approach compares every pair of buildings or blocks, resulting in a quadratic time complexity. But the two-pointer traverses the elevation map once from both ends, so that is a linear time complexity. In terms of efficiency, brute force is inefficient because for large input arrays, it takes up quadratic time complexity and it has a lot of nested loops and redundant calculations. But two-pointer is more efficient. It calculates it without you making any redundant calculations, and it's much faster for larger arrays. Applicability: brute force is suitable for small input sizes or when efficiency is not going to be of a concern, and two-pointer is preferred for this specific problem of trapping water because it will work well even with larger input arrays. Real-world use cases and examples. It can be used in urban drainage systems. So assume you have a high population density where you face issues of urban flooding because of heavy rainfall. Trapped rainwater contributes to this problem. This is significant because calculating this rainwater helps designers plan and design a more effective system to mitigate flooding and prevent damage to property. Land developments. Developers and land planners need to understand the flow of water and accumulation when dividing land for any kind of use. And terrain with trapped rainwater can affect these land use decisions. So you have to have accurate calculations of trapped rainwater for land development plans, infrastructure design, and water management. Trapped rainwater in areas prone to natural disasters like hurricanes or typhoons can make flooding worse. So emergency response planning relies on accurate rainfall accumulation data. So precise assessment of trapped rainwater supports disaster preparedness, including evacuations and resource allocation. Environmental conservation. It helps us understand how rainwater accumulates in depressions or natural basins, which is crucial for assessing the ecosystem's health and for conserving water resources. It can sustain flora and fauna, making it essential for preserving biodiversity. Thank you.